All right, so today we'll start out pretty much doing a lot of Excel work. We'll kind of work in the sampling, which is the next topic that we want to move on to. So if we go to the Zoom page, under Files, in-class data, where is it at? Oh, it should be up here. Did I not drop it in here? Hold on. Guess I'll do it right now. Let's go to the Indiana weather data file in there. So in that in-class data kind of folder, there should be this Indiana weather data now. I just dropped in there, so if you're looking at it, you can kind of refresh. Once you open it up, you've got several different worksheets. So I think the first one that we're going to start on is just this one that says rain. We can do temperature. Let's do rain first. I think this one's a little bit easier to kind of think about. So I'm going to zoom in on this so we can all see it a little bit better. Okay. So the setup is we have this data, right, for the last 100-some years, and we have recorded monthly rainfall in each one of these months. Okay. So I also have kind of the annual, like the average monthly rainfall for the year here in this column O. So I'm going to get rid of this and show you how we can kind of rebuild it and like what exactly it all means. So let's get rid of all that. So maybe we want to label these a little bit. I'm first going to find the mean. I'm then going to find the standard deviation. Okay? And actually, if I wanted to, I could find the variance as well. So first I'm just going to do it for the overall kind of monthly rainfall. So I showed you a picture of this. Let me see if it was, I'd have it on here. Yeah, so here, right, we said it was pretty close to a normal distribution. Right? So we'll go to that rain worksheet. And if we use the average function, I can find the average annual rainfall. Okay? So I select that column, Control Shift down arrow or Command Shift down arrow on a Mac. Hit enter and it'll send me back up here, and sure enough, I've got the mean kind of monthly rainfall. I could also do stdev.s, kind of treating this as sample data, and I could easily find kind of the standard deviation, not of December, but of annual kind of monthly rainfall as well, by simply selecting that variable, or the entire column of data again. Right? So I've got my mean, I've got my standard deviation. I could do the variance here as well, right? All I would do is what? So not the square root, right? I've got the standard deviation, so I actually would want to take this and square it, right? Or raise it to the second power. Yep. Usually we find the variance first, and then we take the square root to the standard deviation, but we can do it in either order. Right? So notice it kind of becomes a little counterintuitive when I have these really low variances, because when I square something, right, if it's below 1, it gets even smaller. Right? So it's kind of this weird range where usually we're used to the standard deviation being less than the variance. Not quite the case here. So I could do this for June, right? I could take the average from June rainfall. So I go back here, select the entire column of June rainfall. You kind of see the mean is a little bit higher than kind of just the across the whole year. I could then also do, actually here, standard deviation. Scroll back a little bit. Grab June rainfall. And then, same kind of idea, I could square that standard deviation to get my variance. Okay? Now, one thing we could think about is if I have these months in order, notice if I copy this over, it's just going to move to the same kind of 2 through 126, but I'm going over one column. So it'll update H to what, column I. And then we look at column I. Oh yeah, that's where July rainfall was. So I could just copy these over and fill out the next couple months. If I wanted to, I could do all 12, but it's kind of easier to see just 4 here on the screen. Right? So I can kind of see there's definitely a difference in the mean each month, kind of shifting it. Looks like June's the highest, and as we kind of progress, it shifts a little bit more towards 0. But notice we'll kind of at the variance, there's also different variation. Right? July has kind of the highest variation rainfall. August has the lowest, right? Okay. So from here, I can start to find kind of like the examples we did last Friday, where we want to say, okay, what's the probability I see 3 inches of rainfall this June? So we've got the mean, the variance, and the standard deviation. So let me see if I can, I think I got to stop this first. I want to try to be able to show you the screen and the dot cam at the same time. So let's see if this will update for us. Nope. Got to get this on the screen in class. Give me 1 second for those of you on Zoom. All right, there we go. So really what we're thinking about here is we have this random variable x, which is June rainfall. Looks like the average is what? Approximately 4.2. Standard deviation is 1.54. And then maybe I'm interested in something like, what's the probability I see 3 inches or less of rainfall, right? Because maybe, you know, I'm thinking about kind of crops here, and if they don't get enough rain in June, if they don't get at least 3 inches, then, you know, we're going to have to do some type of artificial kind of, you know, make sure we get out there and make sure they're getting enough water. So I'm clearly not a farmer. So we've got 3 inches here. I want to know what's the probability I see 3 inches or less, right? So the steps that I'm going to have to take, this black isn't showing up too good, so I don't want to draw these distributions in different colors. So what we're going to have to do is turn that value of 3 into a z-score, look that up in the table, and we can find the area to the left, right? And the equation that we had for the z-score was just take the x value you're interested in, subtract the mean, divide by the standard deviation. Well, we have both those things. So we can do all of this in Excel. And in fact, I'll show you how to kind of do it the hard way and then the easier way. So the first thing I'm going to do, oops, not screw up that, there we go. First thing I'm going to do is, okay, look, I've got this cutoff value I'm interested in of 3. Right? So I'm going to turn that into a z-score. How do I do that? Well, I take that value, I subtract the mean, and I divide by my standard deviation. Right? So I'm just kind of using Excel to basically do what I would have to do on a calculator, right? Do the kind of math for me as a calculator would. Once I have that z-score, right, and if you think about here, it makes sense that it's negative because 3 is below the mean. In fact, if the standard deviation is 1.5, it's 1.2, it's just under 1 standard deviation below. So almost 0.8, right, 0.78. So what's the probability I saw that z-score or anything less than it? Right? Well, that's where we can use this norm.s.dist function. Okay? So all you do is tell it the z-score, and then we will always use comma 1. So when I make this 0, if I didn't want this cumulative, theoretically, what should this value actually be? The probability of seeing exactly 3 should be 0, yeah, right? Probability of any one number is 0, but we can find the probability being less than, or like a certain interval, right? And this was the idea that there's truly an infinite number of possible values we could see here. So the probability of any one value is 0, but the probability over an interval is going to be non-zero, which, as we said, kind of confusing, but that's what it is. So putting 0 in here doesn't make any sense. We're always going to want this to be cumulative, right? We're always going to want it. It's basically going to work just like that standard normal table we were using, right? What this function is going to do is it's going to look up that z-score of negative 0.77975 and basically integrate that probability density function and give us the area under the curve, which is essentially what the table was doing, right? They just had kind of already done all of the work for the kind of 2 decimals and to kind of have those all in one table. But in Excel, I can use any decimal level I want, right? Because it's actually kind of doing the integration as opposed to kind of just looking it up in the table. But it's the same sort of idea, right? It's still returning to us the probability of seeing that z-score or anything below it. So I hit enter, and I get a probability of about 0.22. Which probably kind of makes sense here. We were about 1 standard deviation away from the mean. The area to the left of the mean should be 0.5. We said there's 0.5 on either side. So that's how we can kind of use Excel instead of having to use that table. right? That physical kind of, well, I say physical, right? The PDF that I typically show you. Right? And sure enough, if we looked up at z-score of about what? If we round to the second decimal, I said it was negative 0.78. So negative 0.7, oh, it's just under here, 8, 0.2177, 0.2177, right? We can get a little bit more exact here, but it's basically the same value I would have found using the table. Okay? Any questions on that? Okay with that? So, I mean, basically, like, this is what we're doing in my hand. We just found this blue area here. But what if instead, like, I always have to make this conversion to the z-scores, right? I have to convert my x value to a z-score. But a nice little shortcut in Excel is, if instead of using that norm.s.dist, I just use norm.dist, right? Norm.s.dist told Excel, use a standard normal distribution, right? I'm telling you the z-score, so find the area under the curve to the left, use a standard normal distribution. Excuse me, the normal distribution, norm.dist says, look, I'm starting out with a normal distribution. It doesn't have a mean of 0 or a variance of 1. It's not standard, right? So I want you to take the value of 3, Excel, use the mean for that variable, or June temperature, comma, use the standard deviation for that variable, or that June rainfall. And then comma, once again, 1, make it cumulative. So what this will do is it'll take that value of 3, turn it into a z-score for you. It does this math behind the scenes, and then returns to you that area to the left. Right? So it kind of just does all the work for you, turns it into a z-score, essentially looks it up in the table, and returns you the probability. So if I do this, I should get exactly the same thing. Okay? So norm.s.dist is if you already have the z-score. Norm.dist will basically calculate the z-score for you, then look it up, kind of that area up in that table, right? Area to the left. Okay? Any questions on that before we keep moving? So, you can imagine if I copy these over, it'll just copy this over to the next cutoff value, the next mean, the next standard deviation. And I could play around with this for, oops, that's not what I want to do. There we go. I could look at this for the next 4 months, right? So we kind of notice here, it's using the cutoff value in September, subtracting the mean, dividing by the standard deviation. Yeah. Oh, you guys, oh, you can see it. Sorry, you have a question?
Yeah. When you find that last value, you type it in, do they have to be in certain order?
Yep. So Excel will kind of remind you, but the first thing, and I know this is kind of small, I don't know if this will actually increase if I zoom in because it's the little thing on the side, but we'll see if it does. No, it doesn't. But the order is the X value you want, right? So that cutoff value of 3, then the mean, comma, then the standard deviation, and then comma that we always use 1 there. Always making it cumulative, so it's just like we're using that physical copy of the table. There's probably a way I can make that. Let me see. Now I'm curious. Can I make this bigger? I don't know if I can. It's probably somewhere else in the settings. But yeah, so the cutoff value, mean, standard deviation, and then always put a 1 here to make it cumulative. So, once I have these referenced, I can start playing around with these values, right? Maybe I'm interested in, okay, I don't know, what's the probability we have only 1 inch of rainfall in June? That probability is really, really low. Well, what's the probability that we see at least 4.2? What should that be really close to? What probability will I get here?
0.
So the z-score you'll get is going to be very close to 0, right? Because you're looking at this cutoff value that is pretty much equal to the mean, right? That z-score is 0, so the area to the left, or the probability of seeing that value or below, should be what? The z-score is 0, the area to the left of it should be, yeah, right? So we'll get a z-score very close to 0, because we're barely any standard deviations away from the mean. which means that the area to the left is about 0.5. Yep. And you could play around with these different cutoff values if you wanted to, you know, for different months. But yeah, that's kind of how you would set something like this up. Okay. Any other questions? I'm going to do a couple more things here. All right. Let's do temperature. I'm going to do things a little bit different than from what I posted. So I'm going to get rid of these values for a second. And let's think about, well, actually, I'll keep these so I can kind of highlight something to you. So I basically did the same thing with rainfall with this temperature. All right, so I put temperature here. So I've got this z-score. It takes that cutoff value, 71.4, subtracts the mean, divides by the standard deviation. So here, notice, if I calculated the variance for some reason instead of the standard deviation, I can divide by the square root of the variance, right? That's just the standard deviation. So they're kind of different way of doing the same thing. We use this norm.s.dist function to find the area to the left of that z-score. And you can use the norm.dist, right? No .s.dist, just the norm.dist. And it'll calculate the z-score for you, then look it up in the table, and then tell you the area to the left, which should be the exact same thing, right? It's the same, you're getting at the same thing, it's just you don't have to do as much of the intermediate work, right? You don't have to actually calculate the z-score. So what if instead I wanted to find the probability that I'm above a certain value, or we can think about here, right? The probability x is above a certain value, or the probability that a z-score, right? We want the area to the right, essentially. Well, if norm.s.dist tells me the area to the left, if I want the area to the right, what should I do? Yeah, all I would have to do is 1 minus that, right? Now, I can do that, right, and kind of calculate first the area to the left, or let's say I didn't have it already, I can put this all in one cell. So use that norm.s.dist, select that z-score, comma 1. That's essentially what I had in this cell right here. But I don't, you know, basically I'm just kind of saving some space in my worksheet, right? Where I can do this all in one cell. Sure enough, I get 1 minus that. Now what I could also do is, if I want the area to the right of a certain x value, right, this cutoff value of 71.4, I can use the norm.dist, right? So now I'm not using the standard normal distribution. I'm using some just regular normal distribution. Here's the cutoff, comma, here's the mean, comma, here's the, oops, standard deviation, and then comma 1, right? So this norm.dist is telling me the area to the left of 71.4. So to get the area to the right, I would subtract that from 1. So that's kind of another way you could use this normal distribution. So you should, there is not any situation in this last category where you should ever put a 0, right? We're always going to use it like it's a cumulative density function, so we're always getting the area to the left of a certain value. Okay? That's a good question. Any other questions on that? In the chat. All right. You know, you can copy this over if you want, but I want to look at a couple other things. So what if I wanted the probability, let's use June temperature still. Let's do between 70 and 72. Okay. So I want the probability of being in between two values. So really what I'm looking for here, right? I'm going to use this old thing I drew. Let's say, I don't know, I think the average is here, what, 70 something, 70.8. So I want the probability I'm in between 70 and 72. Right? Well, this is one of those where we said if I take the area to the left of 70 and the area to the left of 72, if I subtract the smaller one from the larger one, I'm left with just what's in between. Right? Or think about it a little bit differently. If I want the probability x is between, oops, oh, I forgot the first one. That x is between 70 than 72, right? Basically, if I had the probability that x is less than 72, that's every single outcome below 72. But I don't want any of the outcomes below 70 to be included in this probability. So what can I do? I just subtract the probability, I guess technically not equals here, but that it's less than 70, right? So I'm getting rid of every single outcome that is below 70, and this includes every single outcome below 72. So what I'll be left with is what's in between 70 and 72. So how can I use Excel to do that? Well, if I had, I could enter this all in one cell, but norm.s.dist, nope, not s, because I don't have these. Use norm.dist. The first cutoff value I'm interested in is 72, right? Comma, select the mean, comma, select the standard deviation, comma 1. So that's going to give me the area to the left of 72, or being less than or equal to 72. So I then want to subtract from that norm.dist. And what I want to subtract is that it's less than 70. So 70, comma, select the mean, comma, select the standard deviation, comma 1. So that's going to take the area to the left of 70 and subtract it from the area to the left of 72, which will leave me just what's in between 70 and 72. So I go ahead and do that. It'll do all that work behind the scenes for me, basically converting both those into z-scores, finding the area to the left of both of them, and then I told it, subtract the smaller one from the larger one. Okay. Any questions on any of this? And I got a little bit lazy here where I didn't enter these in the cells. I didn't enter 70 and 72. So if I had entered those in the cells and had cell references, I could just kind of start playing around with those and updating this probability pretty quickly. Okay. Any questions over any of that? Any of this Excel stuff? Okay with this? All right. So, let's go here. I'm going to delete this and this. So, let's start out with this kind of information. This is going to go along with the problems that we worked on Friday, basically. Right? So we had some of these examples where I had a mean of 72 and a variance of 64. Right? This was that exam score example, right? So the average test score is 72, the variance is 64. Right? What if I want to work in reverse? Right? So what if instead of giving you some cutoff score, like what's the probability somebody got a, 67 or lower on this exam, right? That would be kind of like what we were just doing, right? I would take that X value, I'd convert it into a Z-score. But what if instead I said, well, look, what's the cutoff score to be kind of in that top 10%, or I'd be above 90% of the other test scores, right? What would that test score be that's kind of the cutoff for that, like being in the top 10% of the test scores? So the area that I want to the left is 0.9. I can do this a couple different ways. So probably the easier way, right? I guess let's think through what we're doing now. Basically, now what we're doing is we know the area to the left we want. So we're going to work in reverse, find the z-score that gives us to that, and then convert that z-score back to a value for our original x variable. Okay? So let me get these caps and these markers before I kill them all. So I know the area to the left is 0.9. What I can do is use this let's use norm.inv first here. So I first tell it what area do I want in that lower left tail. Here, I want it to be the cutoff for the top 10%, which would mean the area to the left of it is 0.9. We then put comma, tell it the mean, comma, tell it the standard deviation. And what this norm.inv will do is it's going to work in reverse. It's going to take the probability or the area you want in the left tail, 0.9. It's going to find the z-score that would give that to you. Then using the mean and the variance of the original x variable, it's going to use that inverse formula we talked about, right? Plug in that z-score, the standard deviation, the mean, and it's going to tell you what that x value is that would give you that z-score that would eventually give you that desired area in the tail, okay? or that, in our case, that 0.9. Now, this example doesn't quite fit up with this drawing in the sense that we're actually looking for an area of 0.9, right? So pretty large, we're probably actually somewhere over here instead. But the same kind of principle applies, right? We tell it the area we want to the left, hit enter. Oh, I did something wrong here. Oh, I'll tell you what I did wrong here. This doesn't make a lot of sense. So I knew this was wrong right away. Why? I mean, I'm looking at this test score, 154 doesn't make a whole lot of sense especially when the average is a 72. So what did I forget to do here? I'm supposed to tell it the standard deviation. So I had the variance is a very easy mistake to make. So instead of just clicking on the variance, I have to actually, if I can type, not put in search, there we go. I need to take the square root of the variance, right? Because this function, norm.inv, needs a standard deviation. So, early on when I said, why are we using, what's the point of the standard deviation? We're just taking the square root, we're just scaling it. Well, in a lot of the functions that you'll do by hand, you want the standard deviation, but also a lot of the arguments you need to use in Excel often want just the standard deviation. So with these norm.dist and these norm.inv functions, we always need to tell the standard deviation, not the variance. So a lot of times that means making sure you take the square root of the variance. Okay. So now I hit enter. This looks a little bit more correct. And this is actually the same value, I think, really close at least, that we were getting when we did this by hand in class. It's going to be a little bit off because we don't have to round the z-score to 2 decimals. Right? Now, if we had wanted to, we could have first said, okay, what's the z-score that gives me that 0.9 in the tail? So when I use that norm.inv, it finds that z-score behind the scenes, but then it plugs everything into my inverse formula so I don't ever really see it, right? I don't know, if for whatever reason I wanted to see it, I can use the norm.s.inv. That basically tells Excel, okay, now I'm working with a standard normal distribution or z-scores. So I want you to tell me the z-score that gives me that area that I want in the tail or the left tail, which we said was 0.9. So now I have that z-score. I could plug everything into this inverse transformation formula. So just take what? The mean plus that z-score multiplied by my standard deviation, so the square root of my variance. This should return to me the same thing that norm.inv function did. It just took me like one more step. I actually just calculated something that, I need the z-score to eventually find what that cutoff value of x was. We don't really need to see it in practical terms. So sure enough, I got the exact same answer. It just took me, took up a little bit more space and showed me something that was an intermediate calculation I really didn't need to see. Right? But I don't know, maybe I wanted to see it, right? It's somewhat interesting that this is, the z-score that I'm using. Oh, it's this one that pops up quite a bit, which is kind of 1.28 or 1.29, right? We'd be in between two on the table there. So, if we ever wanted to see it, we could do it this way as well. Okay. Any questions on this? Now, one thing that doesn't really help me a lot in the sense that if I took out this 0.9, and maybe I want to use the value and kind of use a cell reference here, this is kind of nice because it'll update for me. The only problem is it doesn't update my label, right? Every time I'm going to have to go in and kind of update this label the way I have it. But if I use that cell reference, now I can start to very quickly, okay, what test score is the cutoff for the bottom 40%? Once again, about 69.97. That's what we found in class. I think actually when we did it by hand, you find 0.98, but that's again, because you have to round it to the second decimal. Excel doesn't ever have to round anything. Right? We had to use that physical table, we were limited to the second decimal. Here, I could start playing around with, what's the 25% cutoff? It tells me that test score. What's the 75th percent cutoff? Oh, why didn't it tell me? Oh, because I put it in the, I was going to say, why didn't it update it there? There we go. Right? It's about a 77.4. What if I put in 0.5 here? What value should I get? So yeah, so I get a z-score of 0, but when I would convert that into my x value, it's just going to be my original mean. So sure enough, I get 72. Yep. So I don't know, it's kind of, I think if you can get a good grasp on using these in Excel, it's way easier than using that physical copy of the table. But, you know, the physical copy of the table is, I think, maybe a little bit more intuitive. There's a little bit less like behind the scenes black box, which means it's less likely you make like an egregious error because like you're kind of going step by step. Whereas in Excel, I put everything into this one function. If I flip-flop the mean and the standard deviation or something like that, I'm going to get a wildly incorrect answer, right? So if I'm comfortable using Excel, yes, it's probably way easier. But, you know, a good check is to be able to do it by hand as well to make sure that if for some reason I don't have the kind of function entered incorrect, I'll be able to kind of recognize that. Any other questions on any of this stuff that we've looked at in Excel? Okay. If we have time at the end of class, I might show you this. It's kind of interesting. It shows the power of Excel. So otherwise, we're going to go on quite a bit of a different kind of discussion. Okay. So the Learn Smart, which you should have kind of read before today's class, was more about kind of sampling, right? So we now know about this standard normal distribution, and it's useful. Like we went through some examples that are kind of interesting. You can imagine I'd want to predict, you know, rainfall or maybe predict the level of sales in the future. However, oftentimes we don't have population data, so we usually only have sample data. So, you know, there's usually two situations, either a finite population or infinite. Usually we're dealing with a finite, right? Even if we're dealing with a number of people in the world, there is a cap on that, right? Infinite is usually going to be something like, you know, some data generated process, which we probably don't have a lot of examples of. So we're going to kind of stick to thinking about these finite populations. Now, it's not possible usually to get population data. You know, even when we try to use a census, we do it every 10 years, and it's still, there's going to be people missing, right? So we're stuck using a sample. So what we want to do, our goal is make sure we can get a sample that is going to be best reflected, or sorry, is going to best reflect the population, right? I want to make sure that my sample, you know, if I'm trying to make a statement about the US population as a whole, I don't want my sample of 100 people to all be over the age of 70, right? That's not representative of the population. So a couple ways we can, you know, protect against having a bad sample. We want to randomly sample, first of all. And we've already kind of got a dose of this, but we're going to call the population size capital N and our sample size lowercase n. This is how we denoted it in like the mean and the variance equations. But capital N is your population size, sample size is lowercase n. So what we could do is we could randomly sample people. Like maybe I'm interested in, you know, I don't know, the average height of a Ball State student. So I start randomly sampling kind of students from the university. The problem is, like, let's say I did it with just you guys are my sample, and I put your names in a hat and I want to draw like 4 of you, right? Well, with a limited number of people, if I want a sample of 4, which is a pretty large amount of the population in terms of the people that are here, if I do with replacement, what's something that is pretty likely to occur? I pull the first name, I write that person's height and name down, put it back in the hat. I pull out another name. Well, if there's only 6 or 7 people in the hat, very likely I'm going to pull the same person, right? So when you do with replacement, it's usually not desirable because now you could have one person kind of having a weight of like 2, right? They would be counting as 2 observations. So usually we want to try to stick with without replacement, right? Once when I'm taking this sample, once I select one person once, they can't be selected again, right? I don't want them to be being weighted higher than the rest of the observations. So I say better here. I'm sure there's situations where with replacement makes more sense, but in the context of almost every example we're going to talk about, without replacement is, I think, 99.9% of people would agree is the better way to go. So, you know, there are a few situations where we would have to do with replacement, but for the most part, we can do without. Yeah. So, you know, if I take this sample from even an infinite population, I just need to make sure a couple things are true. Well, I need to make sure that what I'm selecting comes from the actual population. If I'm interested in US income and I take a random sample of 1,000 people, well, that's okay if they're all Americans, right? If I randomly select someone from Canada, well, why the hell are they in my sample? They're not even part of the population I'm interested in, right? So that's an easy one. They need to be selected independently. This usually is not like difficult to not break this rule. Sometimes you usually break it because you're lazy, right? If maybe I you know, I'm doing house calls or for a survey, and I finally get somebody to actually answer the phone. Maybe I ask if there's anybody else in the household who wants to take the survey. Well, that's a problem because now having those two people in the same, they're not independent, right? I wouldn't have gotten the one without the other. So we got to make sure we don't do that, but that's almost never going to be an issue. What could be more of an issue is even if I randomly sample, right? Well, for sure, if I randomly sample, I am not guaranteed that the characteristics of my sample look like the population. So think about if I randomly sampled 100 people, and maybe I did it, you know, I don't know, using some type of a directory, and I just happen to, these 100 people I randomly sample, I end up with the majority of them kind of live in, I don't know, the southeast of America. So maybe like 75 of them. Well, I now know my sample isn't going to be reflective of the characteristics of my population because I know 75% of the population doesn't live in the southeast, right? So, you know, I might want to make sure my sample has, I don't know, 25 people from the southeast, 25 people from the southwest, 25 people from the north, you know, however, or doing it in a way in which it matches what the population looks like. Right? So what I'll do there is kind of divide the population into non-overlapping groups. Okay? So I use kind of a geography example first. I think that's not what I wanted to do here. So let's think about, instead of geography, let's say I end up with, here's a good one. So this is making some simplifying kind of choices here, but let's assume for a second that gender is binary and that we only have kind of male females in our sample, right? We know that on average, if we look at the population, it's about 50-50, right? So if I end up with a sample that has, you know, a sample of size 100 with 90 males and only 10 females, I know that sample looks nothing like my population. So what I might do is kind of create these different groups and randomly sample like 50 women and then randomly sample 50 men, then put those two samples together to get a sample of size 100. And now I know that sample of size 100 has a gender makeup that looks similar to my population. Or I could think about doing this by age, right? Maybe I start breaking up the age groups into, you know, 0 to 10, 11 to 20, 21 to 30, and then I randomly sample a number of people from each age category that matches what the population would be, right? So I might, you know, randomly sample 10 40 to 49-year-olds and maybe only like 3 71 to 80-year-olds, right? Because I want to make sure the makeup looks similar to what the population is. So this idea of creating these stratum is just these non-overlapping groups, right? These different age categories, or I kind of do, I could do this by, you know, income brackets. I want to make sure I have a sample that has an income distribution that looks similar to the US population as a whole. And then from each of these, you know, groups, these age categories or these income categories, I randomly sample from each one and then put them all together to get my full sample, right? So this is the idea of 50 females, 50 males, put them together to get a 100 size sample that I now know, at least in this one characteristic, will match my population, right? And, you know, if I'm thinking about something like, I don't know, looking for the average height of the US population, well, then I definitely want to make sure my gender makeup of my sample looks like the population because I know that the average height kind of varies between those two groups, right? So, you know, you can do this a lot of times, you know, do it by age, gender, income. I'm sure there's plenty of other examples we could think about where it makes sense to break them up into these different groups to make sure that my sample looks like my population. Right? Any questions on this idea? Shouldn't be too bad. So the next one is basically the same exact idea, cluster random sampling, except for instead of breaking it up by some characteristic about the data, we usually try to focus on like subpopulations. So maybe, you know, it's easier for me, I'm in a lot of these big cities, right? Maybe it's easier for me to randomly sample 10 people from like each big, you know, the, I don't know, major city in each state, and then throw all those samples of size 10 into the same kind of sample where I'd have what, 10 times 50, so a 500 person sample. But I you know, divided up the population into these subpopulations, right? Each of the biggest cities in each state. Right? That way, when I throw them all together, I know I have kind of this smaller scaled version of the population. Right? Now, this becomes a problem if I think that things vary wildly across across these cities and whatever statistics I'm interested in measuring. But it is another method we can use to ensure that at least we're getting people from all around the country, right? At least we're making sure that each state is represented, right? So if we're not as focused on certain characteristics, but we want to make sure that every single state or like kind of all these different regions are represented, this cluster random sampling makes a little bit more sense. So I kind of already explained, right? It's usually used in geography, where we take all these different little samples from each cluster and then throw them all together to get our bigger sample. Now, we're not really going to be doing a lot of this in this class, right? This is kind of more like you probably take like a survey class, and they'll teach you, how, in practice, how do I go out and sample these 10 people from every city or things like that. But I just want to kind of make sure we start thinking about, we want a sample that looks like the population. So, on these political polls, like from the fall, you can think about, I want to make sure that every region of the country is represented, because I know that political leanings vary wildly. If I look at the West versus the Northeast versus the South versus the Midwest, so I might break the U.S. up into regions and then do my, maybe phone calls to make sure I have each region equally represented, or each region represented by whatever percent of the population they are. Right? So it's a pretty common application we see of this. I don't know why I even have this in here, but just a reminder, we're doing this sampling because we can't get population data. So what could go wrong? Even if we have this, random sampling, cluster sampling, we do it without replacement, we do everything right, kind of what could go wrong here? So I think we'll have enough time to get through this today, and then we'll kind of pick up with some other examples next class. But the 1936 presidential election, Alf Landon was the guy that lost to Roosevelt, right, or to FDR. So first of all, just a great name. I'm sure it's not, it would be awesome if it was still popular today. But, what was interesting about this presidential candidate was, ahead of time, there's this thing, my grandma used to get this little book, this little literary digest poll, and they sent out these mailers to people, and 10 million mailers, right, which is like, a pretty good size of the U.S. population, right? It's a pretty big sample, 10 million people. I mean, they didn't get all 10 million to respond, but still, 2.5 million people in your sample is a pretty big sample. They were really, and also, I don't know if any of you have from other classes talked about surveys or a psych class tried to, run your own. A 25% response rate is pretty good, right? So they were thrilled by this, right? And if they looked at those mailers and kind of asked people who they were planning to vote for, they predicted this huge landslide, right? That Alf Landon was going to win, 57% of the popular vote and 370 of the electoral votes, right? So huge landslide victory. What actually happened? Roosevelt, talk about a landslide, won nearly all the electoral votes, right? 523, okay? So, how did they get this wrong, right? So like, were they making math errors in this calculation? Is there something about treating this as a sample instead of a population? Or start to make a little more sense, well, do they mail the postcards only to Republicans, right? So Alf Landon was the Republican candidate. If the 2.5 million people that responded were all Republicans, well, then for sure, my results are going to be skewed, right? It's pretty easy to make sure this doesn't happen, so it doesn't seem like maybe that's the case. But were Republicans more likely to respond? So maybe it's not like I sent 10 million mailers to just Republicans. I sent 5 million to Republicans, 5 million to Democrats. What if 0 of the Democrats responded and 2.5 million of the Republicans? Well, that's still going to end up with a sample that doesn't look like the population as a whole. We know it's about a 50-50 split at any given point in time, right? In this case, it was a little more than 50-50, leaning quite a bit more towards FDR, but at least we know it should be somewhere around there, right? So what these two kind of ideas that I just mentioned are the selection, the non-response bias. So if I just sent the mailers to only Republicans, that would be a selection bias. Part of my selection process, I was over-selecting from that one group, right? I know that, in terms of looking at people who actually go vote, it's about 50%, registered Republican, 50% registered Democrat, or, 50% who lean right and 50% who lean left, if you want to think about it that way. So if I over-selected Republicans, that's a selection bias. I systematically selected, right, a group, so now they're over-represented in my sample. Non-response bias would be the idea that even if I sent 5 million mailers to Republicans, 5 million to Democrats, if Republicans are the only ones who respond, I'm still going to end up with a bias, which is this non-response bias. That there was one group that was systematically not responding, right, or not being selected because of, you know, whatever my process is, right? I guess here it's just sending them the surveys back. Okay? So, where are we at? It's like 5 minutes. Okay. So, where we go here? So, what ended up happening was, how were these? Well, think about the selection bias first. How did they select who to send these mailers to? Well, they used names from that were both cross-listed in both a telephone book and in car registration. So the only people that they had in this data set were names that were both in these telephone books and in this large, I guess, data set of car registrations, right? Well, who owned telephones and cars in 1936? Rich people, yeah. Like, not many people had cars to begin with in 1936. And the thing about having your own phone, I mean, not only will you get kind of the wealthy here, who was more likely to have a phone in 1936? Well, really wealthy people, but also, if you look out people that lived kind of outside the city, right? It was way less likely that you're going to have your own telephone line already in 1936. Hell, a lot of people use like the same line, right? There was like, I forget they call them, I don't know if it was group lines or something, where a whole country block was only one person could be using that line at a time. So you already know you're going to get more wealthy people and more kind of urban or inner city people, right? Which, tend to see that rural areas tend to vote a little bit more right. And so you're going to have kind of a skewed sample here, right? So you know that you're going to get kind of the wealthier individuals kind of living in big cities. And so maybe we kind of think about, because of this, at the time, usually kind of wealthier individuals, we tend to see there's a little bit more right-leaning kind of voting habits, right? To boil it down easy, probably trying to protect their money and pay less taxes. But so we know we're going to have a sample that's going to lean more right because we were only sending mailers to kind of wealthier, the upper half of that wealth distribution or income distribution. So sure enough, we look at this, and of the who had a car and telephone, this paper went back like years later and found some of these people in the original survey and asked them who they actually voted for. Or they took a random sample of people who didn't have a car or a telephone at the time and asked them who they actually voted for. So for people who owned a car and telephone, 53% actually ended up voting for Landon. So the prediction was a little bit off, but it still would have been right that Landon would have won. However, if you only look at individuals who owned a car or only owned a telephone, so even if they hadn't, built this out, the mailers based off owning both, that you just owned one, the people who just owned one or the other, about 60% ended up voting for Roosevelt, so in the opposite direction. And then if you had neither, right, so probably low income, kind of probably more likely to live out in the country, actually 73% of people ended up voting for Roosevelt in that category. Right? But because we were using this method to send out the mailers, we got a skewed result. Okay? So that's our selection bias. I think I'll leave it there. We'll pick up on non-response bias from this example on Wednesday. And then we'll go through some other things talking about biases and then start to talk about properties, if I can get down here, of kind of our sample distribution, right? What does the distribution of our sample means? Right? So we will do that on Wednesday. I posted that Next Connect homework last Friday, so start working on that. Probably won't be able to get a whole lot kind of further into it after today, but especially by the end of this week, we should have covered almost all the material that we would need to get the entire thing done. Okay? But for right now, you can probably get through like the first half. All right, I will see you guys on, I'll post an online quiz that's due before we meet class on Wednesday. Other than that, enjoy this beautiful weather, and I'll see you guys on Wednesday.